Imagine teaching a robot to walk, but every time it tries to take a step, there's a random delay, like it's stuck in a traffic jam between thinking and moving. That's the real-world challenge researchers are tackling in reinforcement learning, where agents learn by doing. But what happens when the environment itself is slow, unpredictable, and hides its delays from the agent? That's the problem this study solves. Let's break it down. In standard AI setups, like training a robot to navigate, we assume the agent sees the world instantly, picks an action, and acts immediately. But in reality, delays are everywhere. Think of a self-driving car. Sensors take time to gather data, the computer processes it, and then the car actually turns the wheel. These delays can vary randomly, and the agent has no idea how long they'll last. Current methods handle this by assuming a worst-case delay, like planning for the slowest possible traffic. But that's overly cautious. What if the real delays are much shorter? You end up with an agent that's stuck in overdrive, wasting resources and missing opportunities. Enter the interaction layer, a smart new framework that lets agents adapt to these hidden delays. Here's how it works. Instead of waiting for the perfect moment, the agent preps a whole matrix of possible actions, like a chef grabbing ingredients before the recipe changes. When delays hit, the system picks the best action from this pre-planned set, even if some commands get lost or arrive out of order. It's like having a backup plan for the unexpected. The researchers also developed ACDA, a model-based algorithm that goes a step further. Instead of relying on a single snapshot of the environment, ACDA uses a distribution of possible states. Think of it as considering multiple future scenarios at once. This lets the agent make smarter choices, even when delays mess with the timing. And here's the kicker. When delays are correlated like consistent network hiccups, ACDA shines, adapting dynamically instead of blindly following a fixed schedule. Testing this on robot locomotion tasks, ACDA outperformed existing methods, proving it's better at handling real-world chaos. The key takeaway: traditional AI assumes perfect timing, but the future is messy. By building systems that adapt to uncertainty, we're one step closer to robots and AI that work seamlessly in our unpredictable world. So next time you see a robot navigating a cluttered room, remember, it's not just learning to move, it's learning to deal with the delays that come with being human. Ever wonder how AI learns to make decisions when things don't always go as planned? Like, what if a robot's action takes a few seconds to happen, or a self-driving car gets delayed in processing sensor data? That's exactly what this research is all about. Today, we're breaking down how AI algorithms handle delays, and why some are way better at adapting than others. Let's start with the basics. In AI, there's something called reinforcement learning. It's how machines learn by trial and error, like a toddler figuring out how to stack blocks. But here's the catch. In the real world, delays are everywhere. Imagine a robot trying to grab a cup. It sees the cup, decides to move, but by the time it acts, the cup might have moved. Or think of a self-driving car that sees a pedestrian, but takes a moment to react. These delays can throw off the whole system. To study this, researchers tested two main models for delays. 1. Gilbert-Elliott. Think of it like a traffic light that randomly switches between green, smooth flow, and red, gridlock. Delays jump between short and long periods, unpredictable but with some patterns. 2. MM1Q. This is like a checkout line where customers arrive randomly and the cashier serves them at a steady pace. Delays here can be super long, no strict rules, just chaos. They compared how AI algorithms performed in two scenarios. Deterministic, no noise. Imagine a perfect world where delays are consistent. The AI's performance dropped at first, but eventually stabilized. Noisy, real-world conditions. Here the AI struggled more over time. Why? Because the delays were unpredictable, and the AI couldn't trust its own actions, like driving with a shaky steering wheel and random traffic jams. The key takeaway: stochastic environments, those with randomness and noise, are crucial for testing AI. Delayed AI algorithms need to handle real-world unpredictability, not just perfect scenarios. But how did they test this? They tweaked a method called BPQL, adding controlled noise to actions using a formula like this. Nu I equals beta times AI max minus AI min times xi. Here, beta is a tiny number like 0.05. Xi is random noise, and the action is clipped to stay within limits. It's like giving a robot a tiny, controlled shake to mimic real-world imperfections. Now let's talk about POMDPs, partially observable Markov decision processes. Think of it as a decision-making tool for systems where you don't have full info. For example, a robot might see part of a room, but not the whole picture. POMDPs help AI make smart choices despite missing data. The study also tested algorithms like ACDA, which outperformed others in unpredictable delay scenarios. Why? Because ACDA adapts dynamically, like a flexible dancer adjusting to unexpected beats. Other methods like BPQL or VDPO struggled when delays changed, showing that adaptability is key. So what's the big picture? In a world full of delays and uncertainty, AI needs to be resilient. Algorithms that can handle randomness, not just perfect conditions, will shape the future of robotics, self-driving cars, and more.